Welcome back. In this video, we're going to go over section 3.5, which is about uniform motion applications. So I want to break down the title a little bit. Applications, of course, means it's story problems, and motion problems mean that there are things that are moving. And the uniform piece, what's uniform about it is that nothing in these problems speeds up or slows down, which is unrealistic, of course, but we've got to start somewhere, and that's where we'll start. Yeah, nothing in here speeds up or slows down. The kinds of problems we'll deal with in this section involve either two things, like two people or two boats or two planes or two trains or two cars going either toward each other or away from each other, or starting out at a certain distance apart and moving toward each other. And going at a couple of different speeds, and we're asked some question about that. Or it could be that there's one person, boat, plane, train, car, or whatever, doing two different things. Like maybe a boat goes upstream and then downstream, or a person walks to town and then back, or a person is in a training for a race, and so they run for a while and then swim for a while. So in short, it's two objects, people, boat, planes, trains, cars, or whatever, doing something, going towards or away from each other, or in the same direction at two different speeds, or one person, boat, plane, train, car, or whatever, doing two different things. Okay, and then all of these problems use the distance equals rate times time formula. So I want to remind you of that first. Distance is equal to rate times time. A couple of little examples. If you walk 4 miles per hour, that's your rate, for 2 hours, you're going to go 8 miles. So 8 miles, that's distance, equals 4 miles per hour times 2 hours. If a conveyor belt moves 3 feet per minute, it will take 5 minutes to move 15 feet. So here the distance is 15 feet. The rate is 3 feet per minute, multiplied by 5 minutes gives you that 15 feet. All right, so that rule or formula we'll use throughout all the problems in this section. Okay, so we want to just kind of jump right in and start some problems then. So as I mentioned, all the problems in this section involve either one person, boat, plane, train, car, or whatever, doing two different things, or two people, boats, planes, trains, cars, or whatever, going toward or away from each other, or in the same direction at two different speeds. So basically here, Jack can drive from his house in Fresno to his grandma's house in 4.5 hours. It takes his mother 6 hours to make the same drive. So the story here is about Jack and his mother. So it's about two different people. Each person is going to have a distance, rate, and time. And so I think it's helpful to organize all of this information in a table, because there's 6 numbers there, right? Jack's distance, Jack's rate, Jack's time, and then his mom's distance, rate, and time. So that's 6 numbers. So I'm going to have a table. I'm going to put a row for Jack and a row for Jack's mom. Across the top, I'm going to label columns for distance, and then rate, and then time. Distance is equal to rate times time. And then I'm going to go through the problem and try to figure out the contents of this table from the text or from calculations we need to make. Okay, so let's try. What we're to find is Jack's speed and his mother's speed. So there's 2 things we need to find here. Again, we're going to do this in just one variable. Here it says Jack drives 20 miles per hour faster than his mother. So Jack's speed is described in terms of his mom's speed. So I'm going to go with X as mom's speed. Notice I want to be really specific here. I'm not going to say just speed, because then you got to say, okay, well, whose speed? Jack's speed or mom's speed? You have to be real specific here. So the X, our variable, is going to be mom's speed. I'm going to put that in the table on the row for mom and the column for rate. Rate is like miles per hour. It's the speed. Okay, and then we're told Jack's speed is 20 miles per hour faster. So his speed will be X plus 20. We're just kind of going through the problem here, trying to fill out the table as much as we can with information from the paragraph. Okay, so here it says Jack can drive from his house in Fresno to his grandma's house in 4.5 hours. So that's Jack's time, isn't it? Right? Jack makes this drive in 4.5 hours. So Jack's time is 4.5 hours. His mother, 6 hours to make the same drive. Okay, and now I think we've used all of the numbers from the problem. So let's think about how we can complete the table. Well, the formula up top will tell us that distance is equal to rate times time. So let's multiply the rate and time columns together, and that will give us our distance. Okay, so distance equals rate times time, and that completes our table. And so where do we go from here is we need to make an equation out of that. The equation an equation says that two things are equal, right? So looking in the problem, what is the same? Well, not the speeds or times, but what's the same is they're both going to grandma's house. That is, the distance is the same, right? Jack goes to grandma's, mom goes to grandma's. The distances are the same. So we're going to set the two distances equal to each other. So we'll have 4.5 x plus 20 will equal 6x. And that's our equation. It says that the distances for both people to go to grandma's are the same. Okay, so here we'll have, on removing parentheses, 4.5x, and then 20 times 4.5 is 90. Okay, and then continuing to solve for x, let's subtract the 4.5x from both sides. So that will be 6x minus 4.5x. 90 is 1.5x's. And then that will make x be 60, right? So 90 divided by 1.5 is going to be our x, and that will be 60. Okay, and so what is 60? Well, good thing I wrote it down. 60 is the mom's speed, right? That's what we wrote down in the beginning for x, right? So mom's speed was the 60 miles per hour. And we wanted to do Jack's speed also. He goes 20 miles per hour faster, so he's going 80 miles per hour. All right, so just to kind of recap the problem, it involved two people doing something, and so each had a distance, rate, and time. So that was 6 numbers, so I put everything in a table. I chose a variable to be one of the things I was looking for and tried to put all the other quantities in the problem in terms of that. And reading through the problem, we were able to complete the table. Once we did that, we had to think about, well, what's going to equal what? Because that's when an equation is it says that two things are equal to each other. Then we solved the equation, which gave us one of our answers, and then we had to think about it a little more to write down the other answer. Okay, let's try one here, another one. So here it says, Ashley goes to college in Minneapolis, 234 miles from her home in Sioux Falls. She wants her parents to bring her some more winter clothes, so they decide to meet at a restaurant on the road between Minneapolis and Sioux Falls. Ashley and her parents both drove 2 hours to the restaurant. Ashley's speed was 7 miles per hour faster, or that should say faster, than her parents' speed. We're to find the two people's speed, Ashley's and her parents. So that's a long paragraph, right? Skipping to the end, of course, we're trying to find the speeds once more. So we'll have distance equals rate times time. We've got Ashley, and we have the parents. Okay, and so it's tempting at first to say the distance is 234 miles, but you got to read through the problem and make sure you know what's going on. Ashley is in Minneapolis, and her home is in Sioux Falls. That's where the parents start out, right? She wants her parents to bring her some more winter clothes. So they're going to be coming from Sioux Falls to Minneapolis. And Ashley is going to go from Minneapolis in the direction of Sioux Falls. Okay, they meet at a restaurant between Minneapolis and Sioux Falls, but we don't know anywhere specifically where that is. Is it halfway between or what? So they're going to meet along the way. Okay, so here what's unknown is Well, it sounds like a couple of things are unknown, but what we're trying to find, what we're asked to find, is Ashley's and her parents' speeds. So I'm going to go with here. It says Ashley's speed was 7 miles per hour faster than her parents' speed. So let's let X be the parent's speed. If you chose otherwise, then you're just going to have different looking work, but you should have ultimately the same answer. So for rate, for parents, we're going to put the X in there. Okay, Ashley's speed is 7 miles per hour faster, so we'll go X plus 7 for her speed. Okay, and then what else? The 234 miles, that is the distance between Minneapolis and Sioux Falls. So we know that the total distance traveled, so add them up, is going to be 234. So the parents and Ashley together are going to travel 234 miles. So I really need an expression for the distance. Okay, times. Okay, they both drove 2 hours to the restaurant. So that's kind of key, right? So they both drove for 2 hours. So then that means that the time on both is 2. Now that we know that the distance equals rate times time, that enables us to figure out the distance. Okay, so the table's completed, and so now we know their distances together. Parents driving from Sioux Falls to the restaurant and Ashley driving from Minneapolis to the restaurant. Together, they must drive that 234 miles. Okay, so there's our equation. Notice after all that with the long paragraph, we ended up with a relatively simple looking equation. That's going to happen a lot. Our equations for these don't end up too bad usually, in other words. Okay, so distribute to remove parentheses. This will give us 4x plus 14 is 234. Taking away the 14, 4x will be 230 minus 14. And that's 216, right? 4x is 216. And so then x is 54. Okay, and that's the parent's speed, right? So the parents go 54. And Ashley is 7 miles per hour faster. So 54 plus 7 is 61. Okay. All right, and that will do it with Ashley and her parents. Okay, let's try this one. This one's interesting. We're solving for time this time. Here it says Pedro and Sandra leave their office in Indio at the same time. Pedro drives east on I-10 at 72 miles per hour, and Sandra goes west on I-10 at 76 miles per hour. How long will it take for them to be 330 miles apart? Okay, so how long questions typically are time, right? Long could mean length too, like how long is your hair? Okay, but long in this context is going to be time. How much time it's going to take in order for them to be 330 miles apart. Okay, so you may want to pause the video and try this yourself and then restart it and see how you did. Okay, so I'm going to make a table as I've been doing with columns for distance, rate, and time. This time we'll have a row for Sandra and for Pedro. And then variable. Okay, so here it says they leave their house at the same time. We want to know how long it's going to take them for them to be this distance apart. So the clocks for both people are the same. So X will be the time. And it's the same time for both. If one person left earlier or later, then they would have different times, of course. But right now, their times are the same. Okay, Pedro goes 72 miles per hour. Sandra goes 76. Okay, since distance equals rate times time, we can figure that Sandra's distance will be 76x, where Pedro's will be 72x. Okay. So now, I guess they're going east and west. Let me draw this horizontally. Okay, so Pedro's going east, Sandra's going west. They started in Indio, right? And they're going in opposite directions. So we know we want to find out, rather, when the total distance between the two ends up being 330 miles. So this is different from the one about Ashley and her parents in that instead of going towards each other, they're going away from each other. And we're still given the distances or the total distance traveled. This time it's going to be 330, but now they're going in opposite directions. Okay, so we have 76x, that's Sanders' distance, plus 72x, that's Pedro's distance, and that should make the 330 miles. Okay, so that's 148. X is 330. So then X is 330 divided by 148. So let's calculate. Okay, so it looks like 2.22 hours. Okay, we could convert that into hours and minutes if we'd like, but I think just saying 2.22 hours is good enough. Okay. All right, and that takes care of that for Pedro and Sandra. Okay, let's try one more. Here it says Sal takes 50 minutes to hike uphill from the parking lot to the lookout tower. It takes him 30 minutes to hike back down to the parking lot. Sal's speed going downhill is 1.2 miles per hour faster than his speed going uphill. We're to find Sal's uphill and downhill speeds. So what's different on this one is that this problem is only about Sal. It's not two people this time. It's just Sal, but this time he's doing two different things. He's going uphill and he's going downhill. So I'm going to have a row for uphill and a row for downhill. Still distance equals rate times time. Okay, and then what else do we know? So the speeds, it says his downhill speed is 1.2 miles per hour faster than his uphill speed. So I'm going to make X be the uphill speed. So uphill and rate, that's X. The speed going downhill is 1.2 miles per hour faster. So that will be X plus 1.2. Okay, and so the other information that we have in the problem is times. The 50 minutes to go uphill and the 30 minutes to go back down. But it would be wrong of me to put 50 and 30 in here because those times are in minutes and our speeds, our rates are in miles per hour. And so we need to make it so that the units match, right? Just to give a simpler example, let's say that you're going 70 miles per hour and you go for 10 minutes. Okay, you wouldn't multiply those together and say you're going 700 miles per hour. No, right? You'd take, let me make this 60 miles per hour so it divides nice. Okay, 60 miles per hour, 10 minutes is a sixth of an hour. You would go 10 miles, right? You'd need to change that 10 minutes into 1/6 of an hour is the point. So here, it takes him 50 minutes to go uphill from the parking lot. So the uphill time is 50 out of 60. There's 60 minutes in an hour. So he's going 50/60ths or 5/6 of an hour. 50 minutes is 5/6 of an hour. Okay. And then the 30 minutes to go back down the hill, 30 minutes is a half an hour, right? So now our times are both in hours. And so you got to be careful with that. Sometimes the units are different. We have to make them match. Okay, the rest of this is going to play out similarly though. 5/6x will be the distance uphill. And then a half of x plus 1.2 will be the distance downhill. Okay, and then thinking it through a bit, this guy, Sal, he starts at the parking lot, he goes up to the lookout tower and then comes back, right? So the distance there and back has to be the same, right? If he's walking from his car to the lookout tower back to the car, it's going to be the same. So the distances are what are equal here. We've got 5/6x equals 1/2 x plus 1.2. All right, so there's our equation. Again, not too bad of an equation. And so let's solve that. So we could distribute to remove parentheses on the right. I think I would like to instead first multiply to clear the fractions out. Okay, but whatever you want, you can do. I'm going to multiply through by 6, which is the LCM of the 2 and the 6. So 6 times 5, 6 will give us 5 on the left side, or rather 5x. Half of 6 is 3. We'll have 3x plus 1.2. Okay, so now the fractions are gone. Let's distribute to remove parentheses. 5x is equal to 3x plus 3.6. We'll subtract 3x from both sides to get 2x is equal to 3.6. Then x is 1.8. Okay, that's his uphill speed. We were to find both speeds. So it's 1.8 miles per hour uphill. And his speed going down is 1.2 miles per hour faster. So 1.8 plus 1.2 is going to be 3. It's 3.0 miles per hour downhill. Okay, so hopefully these are getting easier. Let's try one more. Okay, so the story here, Lori's training to compete in a triathlon. That should probably be triathlon. I'll fix that later. She left her house at 6 o'clock and ran until 7:30. Then she rode her bike until 9:45. Overall, she covered a distance of 51 miles. We have her speed biking is 1.6 times her running speed. We're to find her biking and running speeds. So take a minute, pause the video, and then try it yourself, and then restart the video and see how you did. All right, so this is what I've got so far. So this time it's one person. It's just Lori doing two different things. She's running and she's bicycling. So I've got a table with 2 rows, one for running and one for biking, and then 3 columns, distance, rate, and time. And I've chosen the variable to be her running speed. We wanted to know both speeds, but we're told her biking speed is 1.6 times her running speed. So the biking speed is described in terms of running speed. So it's going to be easier if we make the variable be the running speed. Okay, so that's what we've got. And then the biking speed is 1.6 times as much. Our last couple of examples, it's been an addition, added on. Okay, but that's what we've got so far. So now, one thing to be careful about this is that we're given clock times and we need to turn this into elapsed times. So thinking about the running first, she goes from 6 o'clock to 7:30. Okay, we're going to assume that that's an hour and a half, not 13 and a half hours. She started in the morning and just ran for an hour and a half, okay? So she ran for 1.5 hours. Make sure I've got that in the run row. Okay, so her running time is 1.5 hours. Okay, then she ran until 7:30. Okay, then she rode her bike until 9:45. So from 7:30 to 9:45, how long is that? This question actually is a part of it that is bugging me. Her bike just happened to be there right when she stopped running. It's kind of weird. But let's say someone came and dropped off her bike for her. Yeah, that's it. So from 7:30 to 9:45, that's the time she spends running. 7:30 until 9:45. So 7:30 to 9:30 would be 2 hours. 7:30 to 9:30 is 2 hours. And then from 9:30 to 9:45 is another 15 minutes, which is another quarter hour. So 2.25 hours. 7:30 to 9:30 is 2 hours. And then from 9:30 to 9:45 is the remaining quarter hour. All right, so on this one, that's the hard part. Okay, is getting from those times into pieces of hour. Okay, because the rest of it's going to be not too bad. Distance running is 1.5x, and then the distance on the bike is 2.25 times 1.6x. Okay, and then overall, she covered a distance of 51 miles. So that means that the running distance plus the bicycling distance has to equal 51 miles. Okay, so then let's go ahead and deal with that. So we've got 1.5x, and then here, calculator, just to save time, 3.6x. That's 51. Combining here, we've got 4, 5.1x, and that's kind of handy, isn't it? It looks like x is just 10 after all that. Okay, so what was x? X was her running speed. So she runs 10 miles per hour, which seems kind of crazy if you ask me, but that's okay. Nobody asked me. Okay, so she runs 10 miles per hour, and then her bicycling speed is 1.6 times that. So 1.6 miles per hour on the bike. Okay, so then just to kind of sum up once again, we have this problems where either you've got two people, planes, boats, trains, cars, whatever, going towards or away from each other, or in the same direction at two different speeds, and we want to know something about that. And or we have one person, boat, plane, train, car, whatever, going two different ways, either upstream and downstream, or to the lookout tower and back, or whatever. And so we end up with six numbers: a distance, rate, and time twice. So we organize that information in a table. As usual, we let our variable stand for one of the things that we're trying to find. We put other quantities in terms of that variable and fill out everything in the table from the paragraph. Then we think about the problem and decide what has to be equal to what, and that helps us produce an equation we can solve. Okay, that takes us to the end of this section on uniform motion problems. As you can tell, probably there's an infinite variety of these. So my advice would be to practice them as much as you can. And then you will start to get a real feel for them. Let me know if you have any questions, and then have a great day.